So as you can see today, we're talking about arc length and areas of revolution. Basically, a curve revolving about an axis is going to create a surface, and then finding the area of that. But before that, we're finding the length of the curve. It's 9.6, and this is how we're going to start. So suppose y equal f of x for x between a and b as the following graph. And by the way, you can take notes, but what I'm writing now, eventually I'm gonna save it as a PDF. I'll put it on e-learning. Also put the video that is gonna be recorded on e-learning as well. So you're welcome to just listen or take notes as well. So let's assume we have a function between two values a and b, and it has a following graph. Something like this. B, that's x-axis, that's y-axis. So what we are interested at, we want to find the length of this curve. So simply, if you assume this is a string, right? This part of the graph is a string. It's a curved string, but we want to find the length of that string. This is what we're going to do. So we're going to calculate the element of length. So let's say L is the total length. Okay. Just like volume, just like area, we find a little portion of the length, and then we sum it up as the number of terms of this sum go to infinity, but the magnitude of each term go to 0, right? And this sum becomes basically integration. So simply you partition this curve to, many small pieces, and you make these pieces small enough that if you zoom in one of them, let's say, for example, we zoom into this one, okay? So zoom in. It's small enough that when you zoom in, it's simply a straight line, right? Zoom in so that it's almost a straight line. Okay. Now, I'm going to call this length DL. That was a terrible D. So DL. And by the way, does anybody have questions? Let me know in chat. Probably chat is the best because I have it on. Okay. So we're going to find this DL. And this is how we're going to do it. And by the way, I'm assuming, writing this or drawing this as parallel to the small piece right there. So if we go ahead and make this right triangle, then starting from here to here, so starting from this point to this point, how is our movement described? Basically, it's like we have moved horizontally that distance, that horizontal distance, I'm going to call it dx because, it's a little element of the x-axis. And the vertical one, I want to call it dy. Now, how do we calculate dl? We use Pythagorean theorem, right? So dl squared equals dx squared plus dy squared. Therefore, dl is the square root. Let me this up a little bit. Is the square root of dx squared plus dy squared, right? Well, for the reason we just explained, so I'm finding the little element of this guy. So I'm going to go ahead and call this up here dl. on the graph. So I want to sum up all of those guys when the length of each DL is very small, but the number of them approaches infinity, and that's nothing but integration. So let me write down that detail. So sum of all these DLs when the length of DL approaches 0, or the magnitude of DL, let's say that, then this becomes the integration. So what's the integration of DL? But DL was nothing but this is square root expression we have right there, dx squared plus dy squared. And we integrate this, of course, from A to B. Okay, so I'm going to rewrite this formula down here one more time. So that's the reference formula. Oops. Square root of dx squared. So you can call it, that's the change on the x squared, and then the change on y squared. Okay. So that's the arc length formula. Arc length formula. And now we can adapt this to, different types of arc length integration based on what kind of graph and functions we get. Because, in fact, we have 3 categories. So let me go ahead and write them down. 1, if you get parametrization. So parametrization, by parametrization, we mean, you have a function x and y, and x is a function of independent variable t. So x equals x of t, and y is y of t. Okay. For example, x equals, cosine of t, and then y equals sine of t for some t between 0 and 2 pi. And here let's assume, t is between a and b. Does anybody know what the graph of this parametrization is? If you know, go ahead and type it in the chat room. What's the graph? Does anybody know what the graph of this parametrization is? Correct. It's a circle. Well done. It's a circle basically with radius 1, right? With the center at the origin. So we're going to find the length of this curve. Of course, the length of this curve, this specific one, is the circumference of the circle, right? In this case, 2 pi. Okay. So if we have a parametrization, I'm going to go ahead and adapt this length formula for parametrization. So what is the independent variable? So here, the independent variable is t. I mean, it could be anything else. It could be r, it could be s, but x and y both at the same time depend on another variable. So in this case, we should be able, to adapt this length integration formula in terms of t, because eventually you want to integrate with respect to the independent variable. And it's very simple. All you have to do, multiply and divide by dt. So think about it. I'm going to do it this way. So you see that dx up there, and dy up there, dx squared and dy squared. So if I multiply by dt and divide by dt, I can go ahead and send the dt and denominator, this guy, and put it under square root. So if that happens, it's going to go underneath the denominators of these two guys, but when it goes inside, it becomes a squared. So you would have dt squared and another dt squared here. So when I do that, I can go ahead and, get rid of this guy. Okay, so squared dt. So this the square root dy over dx dt dy over dt squared times dt is the same as this one up here. Exactly the same. Well, now if we integrate this from t equal a to t equal b, right, then we simply have a length formula for parameterization. So that's the formula for the length, arc length, in the case of a parameterization. Let's go ahead and do an example. In fact, let's go ahead and do the example for this one right here, example. Okay. Watching, guys? So, example. Find the arc length of x equals, and let's throw some radius in there. So let's say 2 cosine t y equals 2 sine t, right? And then let's go one complete revolution, 0 to 2 pi for t. Okay. So what do we need in this formula? We need the derivatives of each x and y respect t. So of course we need x prime of t, or dx over dt. Let's write it that way. Doesn't matter. So dx over dt, which equals negative 2 sine t. We need dy over dt, which is 2 cosine t, right? And now let me go to the next column. So by the way, the setup of this page is it's a letter, or A4, and then I split it up to 2 columns. So that's the left column. Now I'm going to zoom in to the right side. Like I have the default percentage here, so shift it. So what we had on the bottom of that column was, so we had the length from 0 to 2 pi. Okay, it was derivative of x with respect to t squared plus derivative with respect to derivative of y with respect to t, and then dt. Well, derivative of x with respect to t was negative 2 sine t, and this guy was 2 cosine t. Let's simplify. 0 to 2 pi. We have 4 sine square t plus this one, 4 cosine square t dt. And what can we do with this? We have 4 sine square plus 4 cosine square. Anything can be factored. As you can see, 4 can be factored. So let's take out 4. So we get sine square t plus cosine square t dt. And someone type what the value of that is. Very nice, Athena. That's 1. So if that's 1, that means under square root we have 4, and square root of 4 is simply 2. So we have 0 2 pi 2 dt. And that's a simple integration of that's 2t and then 0 to 2 pi, which is 4 pi. And it makes sense. It's a circle with radius 2, right? The circumference of radius of a circle is 2 pi r. So this is indeed 2 pi times r. In our case, r was the radius, right? Good. Now, if we So that was in the case of, parameterization. So the second one is the normal that we see all the time, like specifically or explicitly y as a function of x, right? As an example, y equal x squared, for example, and then x between 0 to 2. In fact, we can graph that, right? That's the parabola, 0 to 2. That's that guy, 0 to 2. So what's the length of that curve? And maybe we'll find it. We'll see. So in this case, derivative is taking respect to x, right? Let's go back to the length formula. In fact, the integrand, what was it? It was dx squared plus dy squared, right? Well, all we have to do, let's go ahead and, think about it. Whatever integration for this case we're going to do, we're going to be integrating with respect to independent variable x, right? So I have to somehow pull out x out of this square root. And it's doable. Go ahead and factor dx under this square root. In fact, dx squared. So you can go ahead and write it as, 1 plus. Let me do bracket underneath. So bracket 1 plus. If you pull out dx, you get a dx squared underneath dy. You guys agree with that? In fact, if you distribute dx squared on these two terms, you get the same expression back. Okay. And now, if you pull out the dx squared out of a square root, you simply get dx. And under square root, you have 1 plus dy over dx squared. And this dy over dx is nothing but the derivative of the function, right? So we can replace that with, f prime of x. Did that make sense? So again, for this function here, right there, y prime, which sometimes we call it dy over dx, is nothing but f prime of x, right? So in this case, length simply becomes square root of 1 plus f prime of x squared dx, and then your limits, is almost the same. In this case, x is what is changing from a to b, or whatever, the limits are for x. So that's the adapted formula for the case when you have y equals f of x, x between a and b. And I can simply imagine if it was a function in terms of y, like if you had x equal gy, you would have the same situation. Instead, your integration would be respect to y, and this function would be g prime of y. In fact, let's go ahead and write that one down. So it's a similar process. So I'm going to write, and if x equals, let's call it gy, y between, let's say c and d, then the length formula for that case becomes, so I'm going to call this case 3. This was 2. It becomes g prime of y squared plus 1, and then dy, y from c to y from d, right? We'll do an example for this one as well. Okay. So let me zoom out and see what the situation is so far. Okay, so we have, let me change the color of n. What do I do? Change the color. Oh, it's right here. So for example, red. So we had one formula here. That was for parameterization, right? And we had this one right here, number 2. That was for the case when we had y equals f of x, and we had the third one when the function was given in terms of y. But you know, structure is the same. And as soon as you set it up, the rest is integration. Okay. So let's do an example. In fact, let's go ahead and do this example. I'm going to circle it, the y equal x squared one. Okay. Any questions so far, guys? I think our pace is good. Am I going fast? Should I go slower? Are you guys alive? Okay. I know I'm good. Very good. Okay. All right. Let's continue with the example. So the example, oops, I forgot to zoom in. So let's delete those because the font size is going to be different. Let's go to 40. So the example was length of y equal x squared. X between, did you say 0 and 2? 0 and 2. Okay. So simply, this is our f of x, right? So we need derivative of that. Of course, we know derivative of that, or y prime is 2x. Okay. Now the length formula is integration from 0 to 2, square root of, 1 plus the derivative, not itself, the derivative, this guy. 2x squared, this whole thing happening under square root, and then dx. Right? So that's it. That's the setup. So setup is good. The rest, you know, is simplify, integrate, whatever technique you need to use, and finish the problem. So in this case, we're going to have 1 plus 4x squared dx. And that's the integration. And let's go ahead and do this integral. Okay. I'm going to go to the new page. Just add a page right there. Probably I have to split it up. Let me go bring my ruler. That's okay. Now let's zoom in 140%. Let's go to the left side of this column all the way to. So continue from that. Length was 0 to 2, 1 plus 4x squared dx. So we do this integration, or should I leave it for you guys? Should we do this integration? Or I want to see 5. Let's do it. Okay, hold on. Okay, calm down. Calm down. At least, can you tell me what techniques we're going to use? We have to use. Any ideas? What kind of trig sub? Trig sub is correct. Inverse trig, right? So we're going to use trig sub. And do you remember how we did it? So trig sub is correct. Now, which trig function are we gonna use for this one? We have three options: sine, secant, tan. Sine is not, because there's not a negative. If it was 1 minus 4x squared, good. Alex got it, 10. Yep. So in this case, we'll let 2x, I don't need parentheses for that. So trig sub 10. And what we do is we let 2x to be tan of, let's use theta. Right? And it makes sense because if you replace it, instead of 2x, it's going to be 1 plus tan squared, which is secant squared, and then becomes secant, right? Okay. So if that happens, what we just explained is going to look like this. Because remember, under the square root, you have 1 plus 2x squared, right? It's becoming 1 plus tan squared theta, which is secant squared theta. So for that reason, the integration of 1 plus 4x squared dx becomes square root of secant squared theta. And we should have calculated something as well. What's dx, guys? Because I have to replace dx. Well, we can find dx from that equation right there, right? So how do I adjust that? So let's do it here. As you can see, x is half of tangent, and if you do dx, it's going to be half of, what is derivative of tangent? That's secant square theta d. Okay, so for that reason, we're going to have half secant square theta d theta. Let's continue. And remember, the limits 0 to 2 were the limits for x, right? So I'm going to emphasize here that those are limits of x, not theta. Unless you want to write 0 to tan inverse of 2. Or half inverse of 2. Okay, let's simplify this. So this one is secant, another secant square becomes secant cube. So we have half secant cube theta d theta. Well, I'm going to leave this one for you guys. In fact, we did it in class. We did it in 2 different methods. Right? Once we did it with a trig integration and it became partial fraction. I think it took the whole class time, the whole 15 minutes for one integration. And the other method was used by parts, right? So I suggest doing by parts, or if you can go back to notes, and then it becomes a loop. So you bring it to the other side, and you find the value for it. Okay. I'm gonna leave it for you guys as exercise. Okay. I think exercise doesn't have to see. Anyway, questions? All right, now let me find, that is it. I'm gonna go to your textbook and see what kind of questions here. I feel bad for sort of abandoning this book. Okay, let's do, I want to find one that it's x in terms of y. Yeah, here's a very simple one. Sam says I'm in the TV room. Okay. Fun. It's okay, Sam. All right, let's do this one. So find the length of x equals root y, right? X equals root y from, let's see, 0 to 4. Okay. So as you can see, this one is a function of y, right? All right. So for that reason, we go ahead and take the derivative of that. In fact, this is our g of y. So g prime of y is, what's the root y? Is 1 over 2 root y, right? And then the length formula becomes integration from 0 to 4. Now let me write down the formula. It was 1 plus g prime of y squared, and then dy. Messed up something. Secant squared. Okay. Then L becomes, so 0 to 4, 1 plus 2, oops, root y squared, and dy. So it's 0 to 4, 1 plus. Okay, if you square that, we get 1 over 2y, right? Y. And that equals to 0 to 4. What do we get for that? We get square root of basically 2y plus 1 over 2y dy, right? Now, how the hell do we do this one? Hold on a second. Someone's trying to make a comment, so let's see. Oh, you're right. So isn't it 1 over 4y? Correct. Correct. My bad, guys. So let me get rid of that. Thank you. So, just the eraser. That one right there. Okay. So that was 1 plus 1 over 4y. So it's going to be 1 over. Is it good now? Okay. How do we do this integral? Well, let's play with it. It's 0 to 4. On top, we have 4y plus 1. And down here, we have 2 root y dy. We good? Well, oh, that was a surface one, wasn't it? So of course it becomes a very non-plausible integration. But actually, it's a very good challenge. So what I would do probably for this one, I would use a substitution. So one suggestion I have is letting t be square root of 4y plus 1 because it's going to become eventually a partial fraction. And then if that solve for y, because 4y plus 1 is t squared, and then y is t squared minus 1 over 4, right? And then we can do dy. dy is t over 2. And put the y down here. It doesn't become a nice one. So let me just stop right there. I'm going to go ahead and raise these ones. And let me leave it right there because the initial integration was the question. Let me tell you what the question is. Question is number 50. So it's the area of the surface generated, because when you do the area, you multiply by something, it's the derivative is going to show up nicely in front of it. So for this one, we just stop here. No, to integrate. Okay. So, to be honest, the book examples are very simple. So for that reason, let me go to another textbook that I'm looking at. That's the calculus by George B. Thomas. Yeah, Alex, we could go by that substitution becomes a partial fraction, but in denominator we're gonna get a square root of t minus 1 and t plus 1. It's not a very pleasing integration. David. So let's do these ones. We'll do one of these, and then we finish the class basically. But we have the office hours right after, so we can take a break for 5 minutes, and then we can do problems. So let's find this one. Find the curve length of y equals x cubed over 3 plus 1 over 4x. Okay, and then x is between 1 and 3. This is number 11 of University Calculus by George B. Thomas. In 6.3. I can probably extract this maybe section of the book and send it to you guys. It has nice examples and like exercise problems. Okay. So, and as you can see, this is a function of x, right? So we need derivative of that. The derivative of this, let's see, it's x squared and then derivative of 1 over 4x, you can call it 1/4 x to the -1, and then use the power formula, so it's 1/4 -1/4 x to the -2. So when it goes down, it becomes minus 1 over 4 x squared, right? So I'm going to go ahead and erase those guys. Okay. All right. Now length is the integration 1 to 3, 1 plus that entire derivative is squared. And what's that derivative? Is x squared minus 1 over 4 x squared dx. What am I doing? I was trying to go down. All right. We'll finish this one. 1 plus, okay. So that's a quantity squared. So of course we're gonna have, let me erase the parentheses. So we're gonna have x to the 4th, right? Plus, or let's do the middle term. The middle term is gonna be 2 times x squared times 1 over 4x squared. So it's gonna be, 2 times x squared and then times 1 over 4x. We already took account for the negative sign. That's why we have negative 2x squared. If it was plus, this would have been, plus 2x squared, 1 over 4x squared. And if you square that, 1 over 4x squared becomes 1 over 16 x to the 4th. Right? Dx. Let me simplify. I'm not going to combine the like terms 1 with the number that I'm going to get in the middle, because that will help you to simplify the next step. So the middle term becomes, as you can see, x squared and x squared cancel out. So we get negative half, right? Plus 1 over 16 over x squared dx. Okay. So I want you to pay attention. That x squared minus 1 over 4x squared became, in fact, this is simple algebra. It became that expression. Okay, so it's x to the 4th minus half. Again, the negative half, the negative sign is becoming, or is coming from that negative sign. That's negative because you have the subtraction of the two terms. And last term is regardless. So if that was a positive, you still have a positive 1 over 16 x to the 4th. Okay, now let's go ahead and add 1 and negative half, which simply becomes plus half. So we have x to the 4th plus half plus 1 over 16 x to the 4th. So as you can see, no change is happening to the first and last term. Only the middle term becomes positive. Okay? Now I'm going to ask you guys a question. Let me go to the next column and write the same expression. Okay? So we ended up with L equals 1 to 3 x to the 4th plus half plus 1 over 16 x to the 4th. Okay? Dx. And let's see what happened. So we had x squared minus 1 over 2x squared. We distributed this, we foiled this, and we got x to the 4th, minus half, and then plus 1 over 16 x to the 4th. Now, I have this guy under square root, and think about it, you want to integrate this. The integration of that looks, terrible. I mean, we don't even know what to do, right? What method, what technique we use, unless we can sort of write this, factor this, and write it as a complete square, and then the square and the square root cancel out. Let's see if it's doable. Well, we just showed this happen, right? Now the expression we have up there is the same thing, except it's plus half. Now you guys can see what it becomes, right? In terms of a complete square, because that's the same exact thing, except the sign has to be positive. That's it. So under square root becomes that expression. Okay? So I'm not going to erase that. So this guy becomes the length setup becomes integration from 1 to 3 under square root. We have x squared plus 1 over 2x squared dx. And now you can see this second power with this square root cancels out. So we have 1 to 3 x squared plus 1 over 2x squared dx. And we can go ahead and integrate now. That's x cubed over 3. And that one is it minus? Yeah, so it's minus 1 over 2x. And then we evaluate this from 1 to 3. In fact, this is the same function we started with, except it was x cubed over 3 plus. Like this sign right here was a plus, right? That's because of the, the form of the function that this curve length integration formula becomes sort of the same function, but with a minus sign. All right, let's go ahead and evaluate that and then finish this. So if you plug 3, we get 27 over 2 minus 1 over 6. And then minus, let's plug 1, so we get 1/3, and then minus 1 over 2. 27, oops, my bad, this should be 3. Someone has a, oh, right, you guys, you're right, it should be 4 on the bottom. So this should be 4. So that's plus 4x squared. Thank you, Alex. Then this should be 4x squared. And then this is minus 1 over 4x. Right? Okay, so for that reason, things are going to change here. Let me see. So we have 27 over 3. Then this is, why did I even have 16? I mean, it was, yeah. So let's see, it's 9 and then 27 divided by 3. That one is negative 1 over 11. So we have negative 1 to 3. That's 12. And that's 4. Is it correct now? So it was 1 over 16x to the 4th. Yep, so it's 4x squared. Antiderivative of that is negative 1 over 4x. If we plug 3, we get 12 in the denominator. Plug 1, we get 4. Okay, good. Thanks, Alex. So subtracting these two, because, they're similar. So we get what? 26 over 3. And then we have negative 1/12 and plus 1/4. That's 3 over 12, if I'm not mistaken. So that's 26 over 3 plus 2 over 12, which is 1 over 6. Can we go further? I mean, let's multiply this by 2, so we get 52 plus 1, 53 over 6, I think. So if I'm making a mistake, let me know. We adjust the... Okay, and we have everybody. Seems like we have to do it online. We can do it in class, in person. You guys want to just leave. Well, it makes sense. You want to go home, but you're home now. So where do you want to go now? Okay. Do you guys have any questions? Okay. So that was it. Uh, I will. So let me go ahead and stop this. 50 minutes and 40.